Welcome to lecture number 8 of the course. So, let us recall that in the last lecture we solved a couple of examples. So, in this lecture we will solve some more examples and then conclude on this topic and move on to the actual nonlinear structural analysis. Okay. So, let us get started. So, this is the example we solved in the last lecture, where there was a support settlement and then there was another example where this was subjected to uniformly distributed load. Okay. So, in this lecture what we will do, we will look at a truss. Okay. So, this is a truss pin jointed, okay. This is a truss and subjected to 2 kilonewton load, right. So, there are how many members? 1, 2, 3, 4, 5 and 6. There is no joint here, right. So, there are 6 members, okay. And if you go back to the first or second lecture, you will see, and if you use that approach, you will see that this is a statically indeterminate truss, okay. But you can determine the external reaction, because here you have got 2 unknowns, here you have got 1 unknown, you have got 3 equations of equilibrium. So, total 3 unknowns, 3 equations of equilibrium, you can determine easily the reactions. But the member forces, well, you have to use any of the methods of structural analysis that we discussed, or here we will use the direct stiffness method, okay. And we will solve it directly in OpenC's, because if you see how many degrees of freedom are there. So, if I mark, so at the structure level, let us say this is my R1, this is my R2, this is my R3, this is R4, R5. So, there are 5 degrees of freedom. Remember, in a truss joint there are only 2 translational degrees of freedom, okay. So, there are 5 degrees of freedom, 6 members, you assembling the stiffness matrix, it is a lot of work by hand calculation. So, we will not do it, we will do it using OpenC's. So, what I am showing here is my element numbering and node numbering scheme. So, element 1 is connected between node 1 and 2, and the local x axis is very important, because this defines the direction of the element, the I and j node. So, this is the local x axis, that means this is node I, this is node j. For element 2, this is my node I, this is my node j, okay, and so on. So, I have identified it. So, the objective is determine the reactions which we have already determined and the member forces. So, let us go directly to OpenC's. So, this is the example, okay. So, what is the change from the example that we have seen earlier? The change is, in the previous example, let me first let this run as I am talking. So, in the previous example, we are looking at a frame where we used elastic beam column element. Every joint had 3 degrees of freedom, 2 translation and 1 rotation. Now, we are talking about a truss where every joint has 2 degrees of freedom, okay. So, what we can do, we can simplify and we can, so up to this is all definition. So, we can simplify and just consider it is a 2D problem. So, NDM is 2 and number of degrees of freedom is equal to 2. Okay. We are not worried about the rotational degrees of freedom. Okay. So, then this initial part is fairly straightforward. I am defining L is equal to 4, H is equal to 3. So, what is L is this length and H is the height. Okay. And then I am creating the nodes 1, 2, 3, 4, and these nodes are as I have numbered here. This is node 1, this is node 2, node 3 and node 4. Okay. And this you clear the memory. So, this is important as I explained, and then you create the node using this for loop. And what are the boundary condition? Remember, you have got only 2 degrees of freedom at each node. So, fix node 1, fix is the command. Okay. It does not mean it is a fixed support. So, fix is the command, fix what? Translation along x, translation along y at node 1. So, it is a pin joint. At node 2, translation along x is 0, means unrestrained, it is free to move, and translation along y is restrained. So, this is pin, this is roller, and this is exactly what we wanted. This is pin and this is roller. Okay. Then, for the truss element, you need a uniaxial material. So, which is linear elastic material with modulus of elasticity E. E I have taken some value. What is the value I have taken? It is defined here 200 GPa, but remember always work in a consistent unit, so that the results, because OpenSys does not give you any results in any unit. Okay. So, once you are consistent, let us say I am working with length unit of meter and force unit of kilonewton. So, my results will always be in that unit. Okay. So, now that is the material definition. Now, coming to the definition of the truss element, how do we create? So, the command is element truss, then element tag, element nodes, then A, then material tag, and then there are some optional arguments which we will discuss in future when we need them. Right now, we do not need them. So, element truss, this is element 1, first element going from node 1 to node 2, and cross sectional area is A, and the material is 1, that has modulus of elasticity E. So, let us see, this is what I wanted or not. Yeah. So, element 1 going from node 1 to node 2, this is what I wanted, right. Similarly, all other elements. Let me explain this element 6. So, what is element 6? Is going from node 2 to 4. So, this is my element 6, this is going from this node to that node. So, local x is in this direction, as I have shown here. Local x is this direction, and this is the local y, it is rotated. Okay. So, similarly, you create all the elements. Now, if you get the basic stiffness, what should you get? You should be getting only a scalar value, as we have seen earlier, because this is A by L. So, basic stiffness for element 1 is 6250. You do A by L, you will get the same number. So, let me also keep running the example. So, I have run up to this point. Now, here this one, let me run this one. Okay. So, now if I run the model, OPS V, plot the model, then it is going to plot the model, show me the node and element numbering that I wanted to use. Okay. So, apply the load. Here, what is the load I am applying? Let me go back to the problem. At this node, that is node 3, in the x direction, okay, I am applying a 2 kilonewton load. So, node 3 in the translational degree of freedom, I am applying P, which is positive, and it is to the right positive. So, therefore, P, and the vertical is 0. Okay. So, this is the load that I am applying, and then these are the standard analysis configuration. We will keep using it for now, and then analyze it, and we will talk about the step later on. So, let me run it, and then we can see the results. Okay. So, these are the reactions printed at node 1. This is my node 1, this is 2 kilonewton to the left, and that is what we expect. If you are applying a 2 kilonewton load to the right here, and this support being a roller, so you need to have 2 kilonewton reaction to the left. Okay. And you can plot the deformed shape. So, this is the deformed shape of the truss. This node moves to the right, this moves to the right and goes down, this moves to the right and goes up a little bit. Okay. And you can draw the axial force diagram. Okay. You can draw the axial force diagram, and that is it. There is no bending moment, no shear force, right. Very simple and straightforward. Okay. So, what happens if I remove one element? So, let us say I comment this out. So, element 6 is not created. So, what I have, what is the truss? Well, it is running. Let me draw it. So, I am saying this is my truss now. This is my truss now, and here is the load. Is it stable? Yes. Statically determinate? Yes. So, we should not have any problem in solving it. Okay. So, let us see, it has solved in the meantime. This is the system, and this is the reflected shape, and you can get the axial forces. Okay. What is happening? Why these are 0 forces? Well, that is what you would get if you consider the equilibrium of this joint. Okay. This and these two members are perpendicular to each other, and then there are no loads. So, what should happen? There cannot be any force, right, because summation f x is equal to 0, summation f y is equal to 0 must be satisfied. Okay. Even if the angle is not 90 degree and there is no load, then what should happen? If two members are meeting at a joint, there are no forces, okay, then they must be 0 force member, and that is what we get here. Okay. Now, let me do one thing. What if I remove this member also? So, I will now remove element 5. What should happen? What do you think? Let us do it. So, let it run. Should it run? No, it should not, because I have made the structure unstable. This is unstable, right? So, it has plotted the model. Now, what is happening? What is happening? How can it solve it? Very interesting to note that OpenSys is giving me a solution of 0, 0, 0, right? No member forces. So, how is the load carried? How is the load carried? The displacement at node 2 is 0. Very interesting. You see that this is a rigid body displacement, isn't it? The truss is going like this. It should have complained. Okay? It should have complained. I could not see anywhere it is complaining. Okay. Very interesting. But in the other case, when I made the structure unstable, it was giving a warning that the stiffness matrix is singular, but now it is not. Okay, let me do one other thing. So, let me get rid of this, get rid of that, and instead let me play with the support. So, support 2 I will go 0, 0. That means what? That means, or instead let us say support 1 is also a roller, only y is restant. Now, should it not complain? It should, because I have made the structure unstable. So, what I have done when it is running, I have made this also a roller. So, the two are roller, then the stiffness matrix is singular, right? It should now complain. There it is. Factorization failed, matrix is singular. That is what we expect. I do not know how it solved the other case when it was also unstable. Okay? Anyhow, so this is how you play with OpenSys and learn on your own, okay, as we keep solving more and more examples. Now, let me do another interesting example. So, this is again the example same as example 1, but there is a little change here. What is the change? So, what I am saying is now that okay, this is a beam column element, this is a beam column element, okay, but this element here it is pinned at support C and at end B also this is pinned. So, if I draw it is something like this. So, you have this beam, let us say this is I section, you have this beam, okay, and then here there is a pin, and then this is how a member is connected. Okay. So, the moment is applied on the beam, this load is applied at the joint. Okay. So, how do I solve this problem? There are two approaches to solve this problem. One is, because we have now seen a truss, we have seen frame. So, for frame every node has 3 degrees of freedom, for truss every node has 2 degrees of freedom. Okay. Now, here we have a mix. So, this element here is basically a truss element, because this is spin, this is spin, it is only axially loaded member. So, how do I do this? I can use two approaches. One is I will model the member BC as a beam column element. That means, I will model this member as a beam column element. So, if I model as a beam column element, then there will not be any change with example 1. How do I simulate this pin connection? Well, to simulate the pin connection, what we have to do? We have to create a dummy node at point B, and then what happens? Let me draw. So, I will define this. So, this is my node 1 and this is my node 2, okay? And then here this is my node 3, and now this cannot be node 2, this cannot be node 2, because then it becomes same as example 1, 2, 3 and so on. Okay? So, what I will do? I will make this node 4, right? What is this distance? This distance is 0. What is the horizontal distance? This distance is also 0. That means, the node 2 and 4 are at the same geometric location. Node 2 is connected by element 1, this is element 1, node 4 is connected by element 2, right. Now, node 2 and 4 are different node, although they are at the same location. So, how do I connect the two? So, I am using 3 degrees of freedom per node. So, then I have to connect the degrees of freedom, this translation here with this translation. The rotation is left out. So, to simulate the pin connection. So, this translation and this translation will be restrained with this translation of node 2 through something called equal degree of freedom constraint. That means, this degree of freedom is identical to that. This degree of freedom is identical to that. That is what we will do. This is one approach. The other approach is we can model the BC as a truss element. So, well, what happens then if I model this as a truss element, but I cannot use certainly DOF 2 for truss, because I have a beam where every node must have 3 degrees of freedom. So, then what happens? So, this is my element 1, okay, this is node 1 and node 2. Now, I am connecting this with that, and this is a truss element, right. This is a truss element. Okay. So, if it is a truss element, then what should happen here? Node 3. Node 3 has 3 degrees of freedom, and a truss element has only 2 degrees of freedom at each node. So, what we have to do? We have to restrain all the degrees of freedom here. Okay. Then this will work. So, this was fixed, and then this has to be fixed. You will say, sir, what does it mean that a truss element is being fixed? Because this node by default has 3 degrees of freedom. Truss is only connecting to the 2 degrees of freedom. So, the third degree of freedom must be restrained. Okay. So, these are the 2 approaches that we will talk about. This I have already explained here. So, no need to draw again. So, let me now go to OpenC's and do this. So, the first one is using, so here is node 4, the dummy node. Okay. Let me run all of it. So, what do you expect? Too many sessions. If you have too many sessions open, then you need to close some of the sessions, then only you can use it. Okay. So, while this is running, let us look at it. This is node 1, 2, 3 and 4. So, node element 2 is connected between node 3 and 4, and node 2 and 4 must be connected by equal degree of freedom. Okay. So, this is pip install OpenC's, and now these are the length and height same as before, because it is basically a modified version of example 1. Okay. So, let me directly go to the point here. So, here now I have introduced this node 4, which is at the same location at node 2. Okay. Then the rest is same as before. So, node 1 and 3 are node 1 is fixed, node 3 is pinned. Okay. So, this is 0. Now, comes the equal degree of freedom. What is the command? R node tag ops.equal DOF. R node tag means the node that I want to retain, the degrees of freedom of the node that I want to retain. So, I want to retain the degrees of freedom of node 2. What is node 2? This is the node that is connected to the beam, and it is often called the master node. Okay. And then node 4 is the C node, that means the constrained out node. The degrees of freedom of node 4, the horizontal and vertical will be constrained out, will be made equal to that of node 2. That is the meaning. Okay. So, node 2 and node 4, and then what are the DOFs? 1 and 2. 1 means horizontal translation, 2 means vertical translation. So, these 2 DOFs are constrained. So, node 4, these DOFs become identical to those of node 2. That is the meaning. Then this is same as before. This is also same as before. Remember, when we are doing elastic beam column, we have to give I, although it is a truss member, because you are modeling it as elastic beam column. Does it affect? No, it does not. Okay. So, the basic stiffness matrix same as before, you can compare and you get the same answer. Okay. So, this is the model. Now, the load is the same as example 1. Let me go to directly to the result. So, this is the reflected shape. Okay. Now, this member, as you can see, the member BC is only shortening in the axial direction. There is no bending, because it is a pin-pin member. Okay. So, you can calculate the basic deformation. So, basic deformation for element 2. What is the basic deformation here? I have created this as an elastic beam column element. So, there will be 3 basic deformation, but look at the numbers. Only the axial is important. For element 2, only axial is meaningful. This is minus 10 raised to the power minus 20, 10 raised to the power minus 20. Okay. So, these are negligibly small as we expect. These are the member forces. Element 2 member force, you only have axial. The moments are 10 raised to the power minus 17, extremely small. Okay. So, this is the axial force diagram. This is the shear force diagram. As you expect, this element must not have any shear force because it is axially loaded. Okay. What about the bending moment? Here it is. The bending moment is like this. By the way, this is the scale for drawing the bending moment diagram. If I change it to 0.5 and rerun it, you will see what happens. Just the diagram gets scaled up and down. Okay. So, you have bending moment only in this. This is a pin-pin member, no bending moment. Okay. Now, let me go to the modified version of this example, where I am now creating modeling this element as a truss element. Okay. So, let it open. Okay. So, here is this same example. Now, you see, I am sorry, this is node 4 is no longer necessary. So, this is 1, 2 and 3, only 3 nodes are necessary. Okay. So, let it install. Yeah, here I have corrected 1, 2 and 3. So, this element 2 will be now created using a truss element. So, these are the same as before. This is everything. See, note, every node has 3 degrees of freedom. Okay. Now, here is what I mentioned, that the node 3 which has 3 degrees of freedom, all 3 must be restrained, okay, because I am connecting it with a truss element, right. And then here this is now a truss element. Okay. We have seen in the previous example how to create a truss element. Okay. And this is the basic stiffness matrix for element 1, which matches with my hand calculation. This is the basic one from OpenSys, matches with the hand calculation. For element 2, you would say, okay, you have created a truss element. So, I am just giving you the same stiffness matrix for a beam column element, where the first entry is A by L for the truss element, and you see this number is matching with OpenSys. Okay. That is what we expect, right. So, you plot the model and then apply the load same as before, perform the analysis, everything, the result, whatever you look at, whether the displacement, whether the member forces, the axial force diagram, shear force diagram or bending moment diagram, between the two approaches, what do you expect? You must get the same result. Okay. Now, I want to just do a quick change in the boundary condition and see what happens if I do not restrain. Let us see how OpenSys handles it. Let me run it. So, node 3, I have a truss element and node 3 is now pin, and see whether OpenSys complains or not. Because in the last case we have seen an unstable truss, it was not complaining. So, therefore, I am curious to see what happens here. No, looks, there it is complaining, you see. Factorization failed, matrix is singular, because that node is connected to a truss element which has 2 DOF, and that node has another additional degree of freedom. So, that must be restrained. So, these are the things you should keep in mind when creating models in OpenSys, otherwise you will struggle, why is the program giving me unstable solution and so on. So, let me go back to this to 1 and run the analysis. Okay. Well, I think that is it for this lecture. Okay. So, we will in the next lecture we will continue looking at nonlinear structural analysis, or we will start basically the nonlinear structural analysis. So far what we have done, we have reviewed the linear structural analysis and we have spent some time understanding the theory for direct stiffness method, how to solve examples by hand calculation, and how we use or how you solve the example in OpenCIS, right. Now, we will get into nonlinear analysis, where we will start with a very simple problem and understand the various sources of nonlinearities and go from there. Thank you. See you in the next lecture.